Okay, since it's already 3 o'clock, let's get started with the class. Welcome everyone to week 12 of the TS session for this course, Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. As it is the case for the past 11 weeks, I am Arjun, who is the TA for the course. So we are finally here to week 12 of this TA session course. This will be the last TA session for this course as it is a 12-week course. So the routine for this is pretty simple. Last we have done this for the past 11 weeks, where I'll be going through a very brief recap of the lectures happened in 12 week 12. And after that, I have curated some problems, sample problems for week 12. As you might know, as you might have, if you have already seen week 12's lectures and if you have started attempting the assignments, you would have seen that there is not much videos for week 12. In fact, there are only 3 videos compared to the 5 videos that we used to get for every other week. And even those 3 videos are the laboratory demonstrations highlighting the concepts that we have already seen in the past few weeks. And the problems that come out of those weeks are also repetitions of whatever that can come out of the past few weeks. So the sample problems will be minimal. In addition to that, what I plan to do is I also have um, we also have the solutions for week 11, which I plan to go through over here. Since the deadline for week 12's assignment is not yet completed, I am afraid that I will not be able to, not in a position to discuss them with you. So, uh, I don't think anyone is in the room right now to do this. So, we'll get started away. I'll get started away with the recap. Okay. So before going on to the week recap, I'll just like to at least give 1 or 2 minutes about the overall course recap. So the course, as we know, it's about optical spectroscopy as well as microscopy. So the whole course in itself deals with optical phenomena, and it deals with uh, basic biological processes or basic processes such as your absorption, fluorescence, as well as your phosphorescence. And initially, what we did was um, instead of looking at it through a classical mechanics perspective, as many other optical courses or optical courses itself used to focus on, we took a diversion from that, and we started looking at it from a quantum mechanical perspective to understand better at how the process of absorption as well as fluorescence came into existence and how they are formed. And even in fluorescence, we came to know how spontaneous emission as well as simulated emission happens, under what conditions do they happen, and we also saw how or why they happen. And later on in the middle weeks, we also came to know why we are studying these processes in detail and how we are able to kind of use these processes to kind of build equipments. And one such equipment that we started to see upon or build upon is called is lasers, which are which use light to stimulate any biological property or biological specimen in nature. So we saw about different kinds of lasers, which are continuous lasers as well as pulse lasers, and we saw what's the main difference between continuous lasers as well as pulse lasers, and what will be the difference in peak power, peak intensity, and average power between them. And even in pulse laser, initially we were looking at um, initially we were looking at very early examples of pulse lasers, and then we focused on going into more advanced or modern forms of pulse lasers, which included your nanosecond to your picosecond and femtosecond lasers. And we also saw a lot of requirements which we need to satisfy in order to go to the in order to go to the narrow range of pulses, picosecond lasers, especially how your laser bandwidth need to be adjusted to in order to produce femtosecond pulses. And we also saw it about lot of examples such as your Nd:YAG laser, helium neon laser, and lithium laser, and so on and so forth. And after studying about lasers, we saw that okay, we have these lasers in hand, we have these instruments in hand. Where and how can we use them? So we saw about how we can use them in microscopes. How does a microscope technically work, and how do lasers in combination with helps us produce beams of light which can be modulated or modulated in order to kind of focus on smaller objects or microscopic objects, and how do we manipulate those beam width and beam profile to kind of image them properly. So with that being said, the last week of the lectures predominantly focused on laboratory demonstrations of the above concepts discussed in the past 11 weeks, where we initially saw about the alignment of beam lasers. So in the first lecture, we saw mostly about how to align a beam laser using your using lengthwise alignment, as well as your typical using in the typical microscopy or laser based setup where we have a bunch of lasers and lens. And after that, we kind of took a in the next video we kind of took a fluorescein dye, and using the fluorescein dye we were able to see in using a one photon fluorescence process, how we are able to visualize the fluorescence coming out of the dye properly a process sheet of a paper. We are able to see that the one photon process eventually leads to the streaking of your absorption process. And in the last video, we kind of also looked at two photon processes using nanosecond laser, femtosecond laser, and we also saw how do we modulate the mode locking to achieve a broader bandwidth, which is actually required by the uncertainty principles for us to produce femtosecond pulses. And in all of these processes, we also saw some of the more general topics such as safety principles, how to maintain your pulse, how to maintain your laser setup, at what height to maintain the laser setup, and how to wear goggles and all those stuff. So this has been the general recap of the course, as well as the um, yeah, this has been a general recap of all the concepts that I've been taught over the course of the week 12, and as well as the overall course. So I will lead right here to have a short doubt session, but I initially thought of having a doubt session, but since no one is in this room, I think I may just proceed over to discuss some of the sample problems uh, that I have sort of curated for this course. So I'll get started. At least for the sample problems part, since they were most of the most of the lectures that we saw, mostly elaborated demonstrations, which were focused on concepts that we have learned. The questions might also be repetitive in nature. So I'll just try to cover them as fast as possible. Yeah, so let's get started. So most of the questions here are kind of theoretical questions, which involve like just basic thinking, basic concepts that we have already seen over and over. So the first question is, in a titanium sapphire laser system, the 530 nanometer pump light is typically generated from 1064 nanometer source through which process? So typically we know that your titanium sapphire laser system has a 1064 nanometer. It has a initial wavelength of 1064 nanometer, but for the lasing system we actually use a 532 nanometer pump light. So basically, how that is achieved is using a crystal which second harmonic generation crystal. So the answer for this question is sorry. So the answer for this question is second harmonic generation crystal. Sorry for the disturbance. I just got a cold. So, so we'll go to the second question. I think we already have clarified over the concept of this. So using a second harmonic generation crystal, the wavelength of the pump light is being reduced by half of the source light. So second question, why does the spectrum of a laser broaden significantly when it transitions from continuous mode to mode locked operation? So this we already saw it's due to the uncertainty principle. So because short pulses, especially the femtosecond pulses, require a large spectral bandwidth. So that's why the spectrum of their laser broaden when it switches to mode locked operation, which is a key component for your pulsed laser generation. So the answer is option B, because short pulses require a large spectral bandwidth. Yeah. This is a question that we have already seen last week. What is the standard voltage used for a TTL high signal to switch a laser diode on? And it is 5 volt. Option C. Fourth question, what internal component is used in a titanium sapphire laser to compensate for dispersion and tune the wavelength? So we are discussing about the internal component which we almost saw, I think, in the um, second lecture or the third lecture of this week. This component is used to compensate for the dispersion as well as to tune the wavelength. So I think tuning the wavelength you already know. We use a two prism system to tune the wavelength. So the answer automatically switches to air prisms and slits. So air prisms are used to tune the wavelength and the slits help in dispersion of light to compensate for the dispersion of light. And the fifth question, the last question probably I think that I have the sample problems. For safety, what is recommended height for laser beams to be maintained on an optical bench? So for safety, what is the recommended height for laser beams to be maintained on an optical bench? Eye level for easier alignment, as high as possible towards the ceiling, waist level to keep eyes out of the plane on the floor. So basically, whatever we saw in the last week, that whatever laser work we are doing, it should be made sure that there should not, whatever laser work, whatever laser beam is coming out of the laser system, it should not be crossing our eye. So definitely you can't have it at eye level for easier alignment. And even the thing is, you can't also have it in the floor. Then there's a problem of electrical hazards, and you can't also have it as high as possible towards the ceiling because it will be tough to handle. So should should it be below eye level, at almost at base level, and out of the eye plane, and it should also be easy to handle. So the option is option C, waist level to keep eyes out of the plane. So that's all I have for the uh, sample problems of the session. Um, since there is no one in the room, I kind of will start again with the discussing the previous week's problems as well. So find out the focal length of. So first question, this is the wherein this is the weak lemons solutions we are discussing about. Find out the focal length of the 60x objective lens, given that the focal length of the tube lens is 200 millimeter. So answer is millimeter, 2 decimal points. So basically, I think I can use this to write here probably. Okay, I think I can write it. So basically, your magnification is given by the formula as the focal length of your tube lens divided by the focal length of the objective lens. So this is basically the formula for using the magnification. So here we have three parameters, out of which two of them we know. One parameter is your magnification, and the other parameter is your focal length of the tube lens, which is 200 millimeter. So technically, your focal length of your objective lens will be equal to focal length of your tube lens divided by your magnification. So basically this will be focal length of tube lens is 200 millimeter divided by your magnification is 60. So if you do the math, you will get the focal length of the objective lens as focal length of the objective lens is 20 by 6, which is around like 3.33 millimeter. So your answer will be, yeah, so your answer will be, sorry, yeah, your answer will be 3.33 millimeter. So I hope everyone got the answer here. So we'll go on to the next question. Okay, one second, I'll just do this. Yeah. So, which of the following statements justify chromatic aberration of objective lens? Yeah. So, chromatic aberration arises. You should say which and all are true, or we should basically find which are all the following statements are true. Since it is an MSQ question, which is a multiple select question, more than one option can be correct. So, chromatic aberration arises as the objective lens refracts different wavelength of rays at different angles, which is pretty much true. And second option, the inability of a lens to bring all the colors in a single focal plane generates the chromatic aberration, which is also true. That's why we get your transfers as well as your longitudinal aberrations. Chromatic aberration can be induced by placing a combination lens, which is true. You can use a planar convex or a planar concave lens to reduce chromatic aberration. And chromatic aberration can be corrected by the planar convex lens, which is true but not entirely true, because that is not the only solution you have to that we have to reduce the chromatic aberration. So we, for this case, we may have to take that as false. So the correct answer will be the first three options. That is, chromatic aberration arises as the objective lens refracts different wavelength at different angles, and the ability of lens to bring all the colors in a single focal plane generates the chromatic aberration. So next question, this is also a numerical question. Find out the focal length of a biconvex lens where R1, R2 is equal to 15 and refractive index of glass is equal to 1.5 and air is 1.0. We should give the answer in millimeter. So for this we should just use the lens maker's formula, which I have provided here, where 1 by f is equal to neta of the refractive index of your glass minus refractive index of your air into 1 by r1 plus 1 by r2, where your r1 and r2 are the radius of curvature of your two sides of your lenses. So substituting all of them, we have neta as 1.5, air, neta of air as 1, and then 1 by 15 and 1 by 15 as 1 by r1 and 1 by r2. If you do all the math, you will get 1 by 15 and 1 by 15 will be 2 by 15. 1.5 minus 1 is be 0.5. 0.5 into 2 again will be 1. So your answer will be 1 by focal length is 1 by 15. So reciprocating on both the sides, you will get focal length as 15 millimeter. So the answer is 15 millimeter. So I hope you get the answer now. So I move on to the next question. Which of the following statements is true with respect to PMT, which is your photomultiplier tube? So in yeah, so in PMT, vacuum has been created to minimize the noise and reduce the low sensitivity or intensity of light with higher sensitivity, which is true with respect to the photomultiplier tube. And quantum efficiency indicates the sensitivity of a PMT, which is also true. The higher the quantum efficiency, the higher the sensitivity of a PMT as well, because the lesser cathodes is going to convert it into more photoelectrons. The purpose of the photo anode is to convert photons to photoelectrons, and it is made of bialkali. Um, this might be true. This might not be entirely true, as we are still not sure what the photo anodes are made of right now. We can discuss about that. The diodes are operated at extremely high voltage, and its main purpose is to amplify the photoelectrons, which is also true. So the correct options are all the options except for option 3, which is that the photo purpose of the photo anode is to convert photons to photoelectrons. So we'll go on to the next question. How is the working distance of an objective defined? So we all know that the working, what to say, the the working distance is will be defined as the distance between the front surface of the lens to the focal plane. So we have a lens, convex or concave. We have to take the front surface of the lens and the focal plane, and the distance between them will be the working distance. So the correct answer is option C. Is defined as the distance between the front surface of the lens to that of the focal plane. So numerical aperture of an objective lens increases or decreases with what? So this also, so numerical aperture will not increase with increase in magnification, because yeah, and numerical aperture decreases with increase in focal length. Yes, does not depend on the magnification. No, it does depend on the magnification. Decreases with increase in working distance for a given aperture of the lens, which is also true. So the correct answer is options B and D, where numerical aperture decreases with increase in focal length as well as increase in working distance for a given aperture. So we can go on to the next question. Immersion me sorry. So immersion media is used between an objective lens and specimen. So immersion media that we see, whether we use oil or water or air, it is just to match the refractive index of the optics with the media and to provide a better resolution. So that's why we're using immersion media. It's a basic question. So our correct option will be option A, to match the refractive index of the optics with the media and increase the numerical aperture as well as provide a better resolution. So which of the following, next question, which of the following is correct about longitudinal and transverse chromatic aberration? So longitudinal, since it's an MSQ, we'll go over the options one by one. Longitudinal aberration is result of magnification. Oh, well, which of the following is correct? Okay, so we just have to choose for the true options. Longitudinal aberration is result of magnification being dependent on the wavelength of the light, which is true. Your longitudinal aberration happens due to wavelength of the light. Transverse aberration result of the magnification being dependent on the polarization of the light, which is false. Longitudinal aberration is result on magnification being dependent on the polarization of the light, which is false again. Transverse aberration is a result of the magnification being dependent on the frequency of the light, which is true. So the correct options are the first option and the last option, where longitudinal aberration is a result of dependent on wavelength of the light, and transverse aberration is dependent on the frequency of the light. Which of the following statements are false about spherical aberration? Which of the following statements are false about spherical aberration? Since it's an MCQ, we'll just go over it. But the difference is we have to choose all the false options. It causes light to focus sharply at a point in space. It's false. It is generated because of the spherical nature of the lens surfaces. It is true, so we won't be choosing it. It is caused by the different refraction and reflection properties of different wavelengths of the light, which is false. It has nothing to do with the surface of the lens, which is false. So the correct options are all the three options except for the option 2. Question number 10. The smallest detectable change in intensity levels of a given pixel in an image is referred to as intensity resolution. So the option is option A. So the next question. An image is considered to be a function of A of x and y, where refers to image contrast. So basically, whatever image you have, the whatever contrast it has, it will be compared to the next point or pixel in the certain image. So it's basically a function of your contrast. So the correct option will be image contrast. So a pixel can be defined as what? Since it's an MSQ, we'll go over all the options. The smallest element of a digital image, which is true. The grain size of photography plate or film, which is false. The area having the same intensity values in the digital image is false. The minimum spatially resolvable element in an image, which is true. So a pixel can be defined as uh, two of the four options, which is option A and option D. This is the smallest element of a digital image and the uh, minimum spatially resolvable element in an image. So question number 13. In an, in an insufficient number of intensity or voltage levels are detected by the DAQ, which is a digital to analog converter, during the digitization of PMT output, then the image constructed from such a signal would have lower sensitivity. So whenever you have insufficient number of voltage levels, then the image constructed will have a very low sensitivity. So the answer is option C. What does a DAQ do? Choose the most appropriate answers. So DAQ basically associates calibrated or scale numeric value to the current voltage generated by a PMT as a function of time, which is true. Convert the analog current or voltage output to a digital value, which is also true. Detects drastic variations in the analog current or voltage output signals and identify them by assigning and calculate, which is also true. So options are yeah. So the options are options A and B. That is, a DAQ associates a calibrated or scaled numeric value to the current or voltage generated by a photomultiplier tube as a function of time, and it also converts the analog current or voltage output to a digital value. And last question, what are the possible causes for streaking artifact or false contouring in an image? And that it's an again MSQ, and the answers for this is slower PMT output digitization by the DAQ, as well as wide dynamic range of DAQ digitization sensitivity with poor digitization resolution. So that's all the answers that we had for week 11. So uh, I think we still have a lot of time for the session to get over. So um, since it's a 2 hour slot, uh, I'll I'll leave this room for the doubt session. If anyone manages to join the room, and in the meantime they can come in anytime and ask for questions or doubts pertaining to the course or with respect to this week's lecture. And if not, then I'm guessing we are here to the end of the TS session series for this course, at least for this edition. So I like to thank you all. It's been a wonderful experience teaching to you all, and for me, honestly, this is the first uh, postgraduate course that I am teaching over NPTEL. I've been a TA for several undergraduate courses, but this is the first postgraduate course that I've been teaching. So I thank you all for giving me the experience to teach that, teach that and resolve some doubts. And I think I, although many of the doubts weren't being cleared through the discussion forum, I check the discussion forum every week, but I don't think I've been getting much enough doubts through that. But some of you have managed to reach out to me through mail and ask some doubts, which I think I'll be able to clarify. So I think from next time it will be a better practice for the participants to put questions in the discussion forum so that a lot of people can engage in a healthy discussion. Um, so apart from that, I don't have anything from my side. I'll keep the session open till 5 for any doubts. So till then, I wish all the best for your exams, and good luck for your future and subsequent courses as well. Yeah. So I'll leave the session for doubts. If you have any doubts, you can ask. Okay, if no one has any doubts, uh, once again, thank you for all your questions, and see you in any other course.